one piece of paper to put down the interpretations of everything you need.
Yeah, I'm down.
Okay,
Yeah, just let me know when.
so we got 2 more days of class, so here's where I'm at. I'm almost done with grading homework 12, and the grader's actually done with the grader's part of 13, so I am hoping before we convene next time I'll have everything graded up to 14. I'm grading 14 by myself, so I anticipate that getting done pretty soon after the math end. So our final exam is during finals week, and I forget when it was. It's Thursday or Friday.
I think
one of
it's
those.
Thursday.
Yeah, that's probably right. So I'm gonna probably send an email around because I really need to. My undergraduate class is bigger, and I need to check with them. You all are welcome to come to the math end. I would also encourage you to maybe help out in the math end, especially if you think you might. Teaching is an important part of you doing graduate school, whether you're going to be an academic or whether you're going to go into industry, because you're going to bring your math skills into industry. You're going to have to teach other people. You're going to have to communicate. So I encourage you to help out. This is certainly not a requirement. You can also come by the math end to get help in the other direction, because I'll be there all day as well. I figured maybe you guys would like kind of a recap session or review session if you like. So I'm probably gonna send around an email like sometime into the week, over the weekend. Y'all look at your schedules. I know you've probably got your own responsibilities with your classes that you've got, plus the class you're taking. So look at your schedule. We'll figure out the time for that as well. Okay, any questions? So the last thing we did was follow theorem. This is a very important theorem in commutative algebra, and thank goodness for it too, because if you have unique factorization with your coefficients, you also get unique factorization in all your polynomials, which is math would not, the commutative algebra would not be as useful as it is if this and a number of other theorems were true. Let me tell you what we get from this. I'm going to put down a couple of corollary sections. Okay, so from this, very easily inductively, it follows that a polynomial ring in invariables is also a UFD, because after all, if R is a UFD, then Rx is a UFD. Well, now Rx is a UFD, so Rxy is a UFD. So now you got 2 variables and so forth and so on. The induction is fairly easy. And in fact, here's the previous corollary on steroids. Okay, that's fine. Then in fact, not only infinitely many variables in any collection of variables that you like is a UFD. And the way this one works is take any particular element out of this. Any particular element involves only finitely many of these variables, because it's a polynomial, and even though you've got infinitely many indeterminates here, a specific element involves only finitely many. And if it involves only finitely many, it's in this thing, essentially. And everything here is a product of primes, and there you go. So that's essentially how this works. Here is a word of caution. I don't think this is in your notes, but I just pass it around just kind of as an item of interest. If R is a UFD, it is not necessarily true that power series rings unique factorization domain. This was discovered around 1968. There's a very famous example and a whole bunch of other kind of sequel papers that did variants on this example for other applications. The result by Samuel, I think. But it is possible. You have to look fairly hard. If you look at Samuel's example, it's fairly sophisticated, but it is possible that you can have unique factorization here, but power series does not. We'll give you a positive result without proof. If R is a principal ideal domain, then so if your coefficients are in a UFD, it's not necessarily good enough, but if your coefficients are a PID, then it works for any finite number of power series variables, just as an item of interest. And remember, if you believe your homework, PIDs are the UFDs that are small, they're one-dimensional or less. And so, and in fact, this example actually, the example that Samuel gave was actually a two-dimensional UFD. So it can fail pretty quickly. Okay. All right, so let me talk a little bit more about polynomials. Definition. Let's suppose that R is commuting with that. Well, I'm sorry, R is okay. R. We say, and we'll say that F of X. So F of X is a polynomial with coefficients in R, and T is, say, some bigger ring that contains it. We say P and T is a root of F of X. Yeah. Let me point out that you can talk about roots in the multivariable case, but if you've got, say, multiple variables, then instead of just a single element, you plug in perhaps two. This can also be extended to the non-commutative case, but depending on what you do with your polynomials, you might have to talk about left roots and right roots. Let me give you the following proposition. If R is commutative with 1, then R in R itself is a root of F of X and Rx. It can only be minus R divided. Okay. This is kind of a fundamental result, as you may guess. Let's go through a quick proof of this. It's a commutative with 1. Actually, let me see here. suppose. Actually, let's also suppose first. R. See an easy way to do this. I'll probably just leave the 0 divided by x as a root. Let's see. Actually, you know what? If you want the if and only if, I'll write that in the notes. Let's say that R is a domain. I'll see if I can improve this. Okay, R is an integral domain, so we'll force it to okay. So here's how I can use the integral domain. An element of note that f of x equals x minus r times g of x plus say t of x. And what I'm using here is Euclidean algorithm because kx actually is a Euclidean domain, right? And so what does this mean? This means that with degree of t of x with t of x equals 0 or degree of t of x less than 1 because we divided by x minus r and x minus r has 1. But notice that r equals 0 and so we'll get 0 equals r minus r times g of r. So r is a root of r. And here that's a constant. So that's 0. Right. Now, what you wanted to argue now is g of x factor in r of x. Because the only thing we know at this point is g of x is actually in k of x. But this argument comes from the fact that this is monic, right? So f of x is a0 plus a1x and x again, which is x minus r times g of x, which is g0 plus g1x. plus Gn minus 1, Xn minus 1. Now, multiplying out the largest component, what you get is Gn minus 1 is in R, because the leading coefficient of this is Gn minus 1, and it has to match An, which is in R. And once you know that, you now have Gn minus 2 minus Rgn minus 1 is in R, but this is in R. So Gn minus 2 is in R, and so forth. The other direction, so in other words, let me write a conclusion here. So f of x equals x minus r, g of x, or g of x. And that's the statement we need, because this is precisely what it means for x minus r to divide f of x. On the other hand, f of x equals x minus r, and g of x is g of x and rx. Okay, so here is another theorem. Theorem 5. This one's kind of a classic. I suspect that you all know this at least intuitively. Let and f of x, then if degree of f of x equals n, then f of x has at most n roots. Suppose we have roots P1, P2, Pk of f of x. So suppose I have any list of k roots. What I want to do is I want to show that that number k of roots that I have is no more than the degree of the polynomial f. And let me also point out that, of course, if f of x is a polynomial with coefficients in R, then it's certainly a polynomial with coefficients in t. So since f of x is a member of Rx, it's certainly a member of Tx. Notice that now, look at, so what this means is, of course, this is using the previous result to show that, indistinct. Of course, here, I mean, distinct roots. Multiple roots we'll have to get around later, but so if f of x is this, then you have x minus t1 times f1 of x, where f1 is in t of x. This is by the previous proposition. Notice that f of t2 is t2 minus t1, f1 of t2. And this is 0 because t2 is assumed to be a root. Now, by the distinctness, this is not 0. And so f of t2, f1 of t2 is 0. So f1 of x minus t2, f2. And what we get is f of x minus t1, x minus t2, f2 of x. See, convection. And n, which is the degree of f of x, must be greater than or equal to. Because every one of these TKs gives you a linear factor of degree 1. And so the number of linear factors has to be less than or equal to the degree. Let me point out that integral domain is very important here. Example here, consider for domains R and times T, the number of roots, counting multiplicities, in T of X and T is less than or equal to. Now, there are many examples like this, but I think it's worth pointing out that, for example, so suppose that R is Z mod 32Z, polynomial now, of course, what you would expect for this polynomial, if I said, okay, how many roots does that have over the rationals? You would tell me, well, it's only got one root, it's 0, and it's got multiplicity 5. Agree? The polynomial x to the 5 has 16 distinct roots. So the correlation degree is not very good here, is it, right? Because in fact, 0 bar, 2 bar, 4 bar, every even bar, they're all roots to this, right? And it gets worse. If R is 2 by 2 matrices over real numbers, then 0 alpha 0 0 is a root of x squared 0 of x squared, we'll say, for all alpha and R. So here you have a quadratic polynomial that has uncountably many roots, which should probably make you a little angry, and is a pretty good advertisement for doing community brains. The next is a theorem that is popularly known as the rational root test. And I'm curious, let me state the theorem. rational root test. Suppose you have a unique factorization domain with quotient field K. And let's look f of x equals a0. Suppose you have polynomials. You have a polynomial with coefficients in R. With I want my constant term to not be 0. Because after all, constant term 0, one root of this polynomial would be 0. You can factor that root out and just reduce to a lower polynomial anyway. If u equals r over s is a root of f of x. So if you have a fraction from the quotient field that's a root of this, then the numerator of that fraction divides R0, or I'm sorry, divides A0. Then how many of you have seen the fractional root test before? Do they teach that in high school?
They do, yeah. That was in my section that I teach.
Oh, okay, fantastic. Oh, you mean like here? What you teach?
No, I student taught.
Oh, I see, okay. So for example, you have let's see. So suppose you have this polynomial here, the rational roots are plus or minus let's say R and S, where R divides 28 and S divides 3. And so there's a number of factors of all these, so you go through all the possibilities and test them. Now, let me make clear that there may be no rational root to this one. Maybe there is, maybe there isn't. All right, but if there is a rational root, it has to be at this point, right? And in fact, I set that one up. See if you can find the rational root of that one. And there may, I don't know if there's 3 rational roots or not. I just set it up to have 1.
Now, what's the nice test for irrational roots?
If there aren't any rational roots.
Yes.
So let's do a proof of this. Those are over S. Well, really what that means is what do I call this thing? A0, A1, R over S, A2, R over S squared, A-N, R over S. Now, the thing to do is to clear out the denominator. And so what I get is, what do I get? A0 Sn, so A1 R Sn minus 1, A2 R squared Sn minus 2, A-N R. well, actually. With that, of course, any rational root, I can assume this because instead of writing 2/4, I can certainly write 1/2 and it gives you the same rational root. And this will make things easier. So the GCD of R and S is 1, right? And so notice that R divides this whole chunk right here. So R divides A0 SN, therefore R divides A0. Because this is a UFD and R and S have no factor in common, so R and SN have no factor in common, forcing R to divide A0. And you do the same trick on this side here. This bit is divisible by S, so I get S divides AN, R to the N, therefore S divides AN. And that's basically it. And it's actually really kind of a useful sort of thing. Okay, now, I think I'm going to talk a little bit about the derivative here. And so, yeah, it's like I'm having a stroke here. No limits. I'm going to just take the derivative like you would, like people in business calculus can do it in their head, right? Take a derivative of polynomials. Now, of course, where that comes from classically in math, the derivative is from this limit notion, right? And it's always been kind of amazing to me that tells something about the slope of the tangent line, but it also purely algebraically tells you something really cool here. So, suppose R is a root of f. And so we have f of x equals x minus r to the n g of x. Here we're over an integral domain, say, so I know that we've got that situation there. Okay. If n is bigger than 1, we say R is a multiple root. Of x, and if n equals 1, we say R is a simple root. And this is, I used the word multiplicity before, but and this is really what we mean by that. Now, I am going to write something down that you all know, and this is called derivative. In fact, in algebra, we call it formal derivative. It's a derivative of a polynomial that you expect. This is useful all over the place, but especially in characteristic P, actually. Definition. 5619. Same K, X K is a polynomial over in R, then the formal derivative of f(x) is exactly what you think. This is K, AK, that's K. Of course, I could start the summation at 0 as well, but if I start at 0, the first term is 0, which needs to be. So the formal derivative is just what you're used to in calculus. Let me give you a theorem that here's here's kind of the algebra magic for the formal derivative. This is 20. Let R be an integral domain and FG and R as X. Let me do your two polynomials. A constants pull out of derivatives, right? You've probably seen this verified from an analysis point of view, perhaps, but it's an easy check. Derivative of the sum is the sum of the derivative. There's the product rule. Again, you probably verified this in calculus before. Here's the chain rule. This is n f to the n minus 1 times x prime. Now, here's kind of the meat to this. So this is probably all familiar territory. But here's an interesting observation. R is a multiple root of f of x. If and only if well, I guess I need that for root. And that gets you multiple. And F, this will be actually kind of useful. We'll see this crop up next semester, if you're still with us. If R is a field, and F and F prime are relatively prime. That is, their only common divisor is 1 up to a unit. Then F has no multiple roots. Okay.
Before you,
Oh, I'm sorry.
no, it's okay. We had the theorem that if x is a root, then x minus r divides f of x. And then we have this theorem here, saying if r is a root of f of x, then the x minus r to the n divides. Is the way that we reconcile these two, that x minus r, we use that x minus r still divides because.
Yeah, X minus R still divides.
X minus R.
The only questions you have is, does it divide it more than once, right? That's what the X minus R at the end is. So if F of, if R is a root, so we're talking integral domains here. If R is a root of F of X, then that means I know that. I know
Yeah.
that
Okay.
much.
I think that's what was confusing me because we said if n equals 1. I just don't think we didn't assume call n like the largest n such as.
Oh, okay, actually, I see what you're saying now, and you're absolutely right. Yes, I should have said, if, so let me correct that, if n equals 1, and R is not a root of G of X. Or another way you seem to be putting it is N is the largest number of powers of
Yeah,
X
okay.
minus R. Yeah, you're right. I was a little sloppy when I wrote that down.
Thank you.
So let's look at this. So let's look at these. Suppose that f of x is x minus r to the n g of x, and then it's greater than or equal to 2. Right? Then I claim that you get this. Note that f of r is 0 for sure. And f prime of r is n x minus r to the n minus 1 g of x plus x minus r to the n g prime of x. And so f prime of r equals 0 as n is greater than or equal to 2. Because I know I get a 0 here because n minus 1 is equal to 1. And on the other hand, so if f of r is 0 and f prime of r is 0, then see if you can work that one out. That was pretty easy as well. And f, part f, suppose r is a field and f prime are relatively prime, then f has no multiple roots. Consider f of x. And here's what you know, then with so suppose R is a root of suppose R is a root of f. This entertains the possibility of multiple roots. G of R is not 0. Thank you, Jared. I'm more careful here. And so what we need to do is show that if f and f prime are relatively prime, then f has no multiple roots. Suppose f and f prime are relatively prime. And if I can figure out what f prime is, just like before, x minus r are relatively prime. Notice that Rx is a PIV sense of field. So if GCD of f and f prime equals 1, then I can write that is a linear combination. Right, 1 is a linear combination of f and f prime. Note that as f of r equals 0, if I plug in r here, I get 1. is 0 plus b of r f prime. So f prime not 0. But f prime of r equals, what does it equal? Let me grab the formula. This is x minus r n prime of x plus n x minus r n minus 1 give x. Therefore, f prime of r, well, this is going to be 0, sure, right? And this is n times r minus r, the n minus 1 to r. But if this is not 0, it must be 1, right? Because otherwise I'm going to get a factor of 0 here. Therefore, r is a root multiplicity. Because the derivative can't be 0. Okay, any questions on that? Okay, so I'm going to give you kind of, this is sort of like a family of these polynomial kind of theorems. Last one here. And this is the rather famous Eisenstein irreducibility criteria. This is called the Eisenstein irreducibility criteria. Suppose R is a UFD. Of course, you'll say if f of x is equal to R0 plus R1x plus R2x squared n. And of course, all my coefficients I'm assuming are actually in the ring R is of degree at least 1, and P is a prime. And P is a non-zero prime in R, such that, here's what my criteria, P divides each coefficient except the leading one, P divides Ri. So P divides every one of these coefficients except the last one. And 2, P does not divide Rn. So I want it actually to not divide the last one. And P squared does not divide R0. Then, if you have this, then f of x is irreducible. So, as an element of the quotient field, polynomials in the quotient field, it's irreducible. And if the GCD of the coefficients, then it's also irreducible in Rx. So in other words, this first step, this criteria here shows that you can't break it down non-trivially. That is, without pulling a constant out. And the last bit says, but if you can't pull anything out of the constants, it's irreducible below. So for example, and if you like Galois theory, number theory, sometimes you need to produce irreducible polynomials quickly on the fly. This is, Eisenstein makes this easy to do. Bang. That thing is an irreducible polynomial over the rationals, plain and simple. Because the prime 2 divides this, 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 and this. It doesn't divide the leading coefficient, and its square 4 does not divide this. So this is what I might call 2 Eisenstein. It's irreducible over the rationals, and since the GCD of the coefficients is 1, I can't suck any constant out. It's irreducible over the integers as well. Okay, any questions on that? Any questions out there? Questions? Okay, you all have a good one, and we will see you by Friday.